Hello students, today we are discussing Unit 4 Vision and Motion. In this unit, we will learn how computer understand the 3D world using 2D images and video sequences. These are all the different contents available in our syllabus. I grouped these contents in important 4 topics. Let's we see one by one. Basically, vision is about understanding shape, depth, and structure, while motion tells us how things move over time. Together, these help in applications like self driving cars, robotics, and augmented reality. The goal is to reconstruct a 3D scene and track motion just like how our human eyes and brain perceive depth. Now, 3D vision is basically how a computer understands the shape and structure of things in space using 2D images. We as humans get depth because our eyes capture slightly different views. Similarly, computers use different projection schemes like perspective or orthographic to recreate this sense of depth. It's like teaching the computer how to see in 3D. There are many ways to estimate 3D shapes from 2D images. Some methods like shape from shading or texture use natural light cues. These techniques help in reconstructing the world around us for applications such as robotics, 3D scanning, or even medical imaging. Now let's talk about projection schemes, one of the core concepts in computer vision. Basically, when we capture a 3D scene using camera, it becomes a 2D image. This process is called projection. So, every photo you take is actually a projection of the real world onto your camera's sensor. Understanding how this happens is very important because if we know how 3D points are projected, we can reverse the process and get back their 3D positions, which is what 3D reconstruction does. There are mainly two types of projection. One is orthographic, another one is perspective. In orthographic projection, all light rays are parallel, so there is no depth effect. It is simple and accurate for technical drawings where depth does not matter. But in perspective projection, rays meet at a single point. This is how cameras our eyes work. Distant objects look smaller, which gives a realistic depth feeling. I tried to explain how these two diagrams can be drawn. First we go to orthographic projection. First I take a simple geometric structure called straight line. It contains two edge points and I can draw one view plane. It is nothing but a screen. I projected a dotted line from this edge point to the view plane. Repeat this same into another edge point also. So these 2 points are parallel to each other. They can hit the one part of the view plane. I connect these two coordinate points, make it as a new line. So this is called orthographic projection. Next I take one square image. It contains 4 edge points. I repeat this process again for all the edges. The projected lines started from this edge point towards the view plane. All these projection lines are parallel to each other. After getting the intersection point to the view plane, I can redraw the image. So I can get the projected part in the screen. Now you understand how this image can be drawn. This is 2D image. In case of 3D image, if you are doing this parallel projection to the view plane, you can get this 2D image. You just recall the definition for the projection. It is converting 3D image into 2D image. So each and every edge point present in this 3D image can be projected towards the screen. We can get the 2D image. Your eye point is present in this part. So from this point of view, you can view this image. You can get this 2D information. I can show in another diagram. So this is the real object. After projection, it can be redrawn like this. You can see this 2D image from this point of angle. So every 3D object looks like a 2D object from a particular angle. This is what you may done in your engineering drawings. You can create different view plane with a different angle of perspection. You can see the same object in a different manner. These projected lines are perpendicular to each other. So this kind of projection is called orthographic projection. Let's move to the perspective projection. I again take the straight line. After the view plane, I can draw one point. This point is called center of projection. From this first edge, I can draw the projected line towards the view plane to reach this center of projection. In the same way, I can draw the another projector line from the second edge point. After finding the intersection point, I can redraw the line. Here the output line is somewhat smaller than the original line. It means this object can be placed somewhat distance from this view plane. If the object is close to the view plane, you can get the bigger image. Now I try to move this straight line is some distance and again create the projector lines from these edges to the center of projection. Now I can get the new intersection point. I can redraw the image. Now I can get the smaller straight line compared to the previous one. So it clearly tells longer objects looks small when compared to the closer objects. But in case of orthographic projection, the distance of the object does not affect the proportion of the original object. So this kind of projection can be used in your engineering drawings, but in realistic images, perspective projections can be used. Now we go for one square image. It contains 4 edge points. I can draw the projector lines toward the view plane and reach the center of projection. Now I can get the new intersection points for these projector lines and redraw this square. Now you understand how this image can be drawn. Now let's see what vanishing line points and horizon line. In perspective projection, when we look at parallel lines like a road, railway track or building edges, they seem to meet a faraway point. So these points is called vanishing point. And this is horizon line. Depending on the direction of the lines, there can be more than one vanishing point. In this figure, we can see 3 vanishing points V1, V2, V3. All these vanishing points lie in one horizontal line called horizon line, which represents the high level or camera height. So, by finding these vanishing points, we can tell if the surface like a road is flat or sloped. This concept is what gives images and 3D scenes their realistic depth effect. Here we can see how a convex lens form an image. In part A, the rays from the object on the right side pass through the lens and meet the other side to form an image. The image is inverted. It means it appears upside down and it formed at the certain distance behind the lens. In part B, the diagram shows a slightly different view. Here the focal plane is imagined in front of the lens. So this is the view plane and this is just a convenient way to think about the projection, as if the image appears non-inverted in front of the lens. The center of the lens marked as C as the center of projection, meaning all light rays seem to pass through this point during image formation. So in short, this figure shows how a convex lens focuses light to form either a real inverted image behind the lens or non-inverted virtual image in front, which is depending on how we visualize it. The next topic is binocular or stereo projection. Just like our two eyes, we can use two cameras to view a 3D scene from slightly different positions. Each camera forms its own 2D image. And because they see the world from slightly different angles, the same object can appear shifted little between these two images. That tiny shift is called disparity. It is denoted as D. It is the key to finding how far away the object. When we measure disparity and how our camera's focal length and the distance between them, called baseline. So the baseline is nothing but distance between these two cameras. And using these terms, we can identify the depth of the camera using this formula. Here f is the focal length. This same idea can be used in our eyes, stereo cameras and robotic vision. We will discuss this technique further in upcoming topic called triangulation under 3D motion. Now let's conclude this part. So in 3D vision we can capture the different 3D objects using the 3D camera, either orthographic projection or perspective projection, and that can be go to the next stage called 3D visualization. The next topic is shape from shading. When we look at a photo, some parts appears bright and some dark. This is called shading. From this shading, we can guess the shape of an object. For example, if light falls on a ball, the part focusing on the light looks bright and the another side looks dark. Even without the depth information, our eyes can sense that is a round object. In computer vision, we try to do the same. The computer studies brightness changes in a single image and estimates how the surface is tilted. This helps in reconstructing 3D shapes. Here I try to draw a sphere, but it looks like a simple circle filled with some color. But if I apply the light information falls on the surface and it's like a sphere. And if I add the shadow, it much more realistic. And the shadow tells where this object is located in that image. For this concept, we can assume the surface is Lambertian surface. A Lambertian surface is a type of surface that reflects light equally in all directions, no matter where we look from. This means it appears equally bright from every viewing angle. Such surfaces scatter light uniformly and do not have shiny reflections. This property is called Lambertian reflectance, where the reflected light intensity remains constant regardless of the observer position. However, even though a Lambertian surface reflects light equally, the brightness of each point still depends on how lights fall on it. That depends on the angle of the incident. According to the Lambert's cosine law, I equal to I naught cos theta. Here, I naught is the intensity of the light. Theta is the angle between incident light as well as surface normal. Surface normal is an imaginary line that can be drawn perpendicular to the surface. If the incident light is directly hit the surface, then the angle becomes 0. So cos 0 becomes 1. So the entire intensity can be obtained as the output. If it has some angle, the value becomes lesser. If it is 90°, that means there is no light incident on this point. So in that case, we have no brightness. So depending upon the angle of incident, that particular part becomes brighter or darker. So the brightness variation happens because of lighting direction, not reflection type. Usually, the reflection can be happened like this. But in 3D visualization, we can assume that the light can be scattered in all directions. Depending upon the angle of incidence, the brightness can be decided in this point. So here the light can be incident in this point. So this point looks brighter. The surrounding points are having different angle of incidence. So using this concept, we can visualize the realistic 3D object. The next concept is photometric stereo. Here we can construct the 3D shape using multiple light sources. Here the same object can be captured by only one camera but with different angle of light incidence. These are the steps to follow to achieve the photometric stereo method. First we capture the images under different lighting. Camera in a fixed position. Record the each and every pixel information and integrate these collected information. Finally visualize the 3D object. The next topic is shape from texture. Texture is nothing but patterns. Most of the real life objects are not in solid colors. They have different patterns. Using this pattern, we should understand the depth of the 3D object. If the pattern looks like this, the nearest texture patterns looks larger, it means it is close to your eyes. Here the pattern size is small, it tells it is somewhere distance away from your eye. So using these size variations, we can give the depth information to the 3D object. The next concept is shape from focus. It is one of the 3D construction technique based on the focus variation. The same object can be captured in different focus settings. From the different focusings, we can identify the sharpest pixels. From this information, we can construct the 3D image. The next topic is active range finding. It's nothing but measuring the distance between a sensor and the object. It uses its own light or sound signal to measure the depth. The topics we already discussed like shape from shading are called passive methods because that uses the ambient light. Ambient light is nothing but the light energy present in the surrounding of the object. The key idea of the active range finding is sending the signal to the object and the depth information can be identified by how long it takes to return back. So that can be calculated by this formula. So the distance can be calculated by speed of the signal into time taken. This value can be divided by 2 because the signal can be reach the object and return back to the source. There are different types can be followed to find active range finding. One is time of flight, triangulation method, and structured light. The next topic is surface representation. So after visualizing the 3D object using the different methodology, we can store that details inside the computer. That is called 3D representation. So the 3D representation is nothing but the surface information of the 3D object can be stored inside the computer. So we should know how to define the 3D surface in a mathematical way. So 3D representation is simply we can store the surface information. There are two types. One is point based representation, another one is volumetric representation. In point based representation, we can collect the different 3D points in the space that can be called as point cloud. Each point can be represented as x, y, z coordinates. Sometimes points may include extra information like color or intensity. The second type is volumetric representation. Compared to previous one, it consumes more space because it not only stores the surface information and also store the complete information of the 3D object. So that can be visualized like this. Each and every cube contains the entire information about the 3D point. So these tiny cubes are called voxels. So each voxels contains the different informations like distance, density or color. So this information can be stored in a data structures present in your computer. The next topic is 3D object recognition. Before this, first we see what is 3D reconstruction. 3D reconstruction is nothing but we can retrieve the data from already stored inside the computer by means of point based representation or volumetric representation. That data can be reconstructed, then it can be identify particular 3D object by 3D object recognition. 3D reconstruction is nothing but recovering the original 3D objects from the stored content from inside your computer. In the 3D representation, we can store the multiple number of images along with the depth information that can be reconstructed and finally made as a 3D object. For constructing the 3D object, your computer should know different poses of the 2D images. The next concept is 3D object recognition. After reconstruction, we can identify the particular 3D object present in the image. That is called 3D recognition. So it comes after the reconstruction process. After recognition, it can tell what are the 3D objects present in the image. The next concept is introduction to motion. So this part discussed about the static images. Now we are moving to analyzing about the moving part of 3D objects. Moving is nothing but with the time sequences we can get the different frames. We should analyze the moving objects because it helps to understand how the objects are move their direction, how much speed and some more information. The movement can be happened from objects or camera movement or both. This movement process can be represented by both the displacement vector dx dy and optical flow. The distance from the camera and the variation in the brightness that illustrate the movement of the object. That movement can be identified different method. First one is triangulation. Triangulation is a basic geometric technique that can be identify the 3D position. These concepts we already discussed in binocular projection as well as one of the method for active range finding. In this method, the light can be projected and reflected back with the different angles and identify the geometric coordinate. In motion analysis, the camera or object can be moved at a particular time. So it creates a multiple views. By the triangulate these views, we can estimate the 3D position. Let's we see this example. If the object is same, but I move the camera from one position into another position, the difference between these two distances is called baseline. The same object can be captured in camera 1 position and camera 2 position in slightly different ways. That difference is called small d and f is the focal length. Then we can identify the depth information. So I will show the clear picture of this concept. Here C1, C2 are the center of the camera 1 and camera 2. In motion analysis, these two are the same camera with different interval of time. So we have the distance between these two, that is called baseline. From these two different angles we can get the different kinds of pixels that can be identified as x1 and x2. These differences are called disparity. This is not a distance between these two. This is the pixel variations from these two images. I can give one numerical example for this. So in this problem, the distance between the two camera can be given as the 0.12 meter. Focal length value also given, it is 800 pixels. And the first and second camera pixels also given, one is 320, another one is 280. Now we want to find the depth information. So first we find the disparity. It is nothing but the variation between these two pixels. So that is 40. Then you can apply this value in this formula. You can get 2.4. So the final result for this question is the depth information for the particular point P is 2.4 meter. You can realize some fact from this equation. If the d value is too small, we can get more depth information. So these are all the different types of triangulation methods. The next topic is called bundle adjustment. Bundle adjustment is nothing but to refine the 3D points in the scene as well as the camera parameters like position, orientation and focal length to make the 3D points as accurate as possible. By simply we can say that bundle adjustment can improve the quality of 3D reconstruction. So we can reconstruct the 3D images from the different angle of the cameras. After the 3D construction, we may get the small errors. We have to adjust the few parameters to get the good quality of reconstruction. So that can be achieved by translation alignment as well as parametric motion. So translation alignment is nothing but to move the object from one position into another position to make the quality 3D reconstruction. So the different objects identified inside the image that may be overlapped to each other, that can be adjusted as to show the 3D objects properly. So these are all the different adjustment methods can be available in the bundle alignment. But we focus only translation. So it is nothing but the original object can be moved into some other points. I will tell how it works. Once I identified the actual image can be shifted into some other location, I want to move it again into its original position. So that I need finding the translation vector. Translation vector is nothing but the difference between the coordinate values from the original position into the new position. Then apply this, we can get the actual location of the object. Let's see one example. So this straight line contains the starting point as well as end point. Take this point as x1, y1, this point as x2, y2. But this image should be shifted into 2 points away from this original position. So I fix the translation vector like this. Tx equal to 2 and ty equal to 2. That means the new coordinate value can be added from the original coordinate value from this translation vector. These two values are old value, that is 2, 2, that can be added with the corresponding translated vector value. You can get the new coordinate. So when you apply xy as 2, 2 with this translation vector, you can get 4, 4. So in the same way, you can apply the endpoint of the straight line to this formula. You can get 4, 12. You can connect these two lines. So now you can able to shift the original position of the line into the new position. So this is called translation alignment. Suppose this is 3D object. You should have the z coordinate values also. So the translation vector looks like this. So the problem may be asked like this. If you have the original value for this point, that may be 2, 3, -4, you want to shift this object into another position. For this, you should know the translation vector. Then apply these values to this formula, you can get the new coordinate value. When you apply this value here, you can get 10, 15 and 6. Sometimes the old value and new value given. You have to find the translation vector value. So if you want to know tx, you can bring this x into this position. So x dash minus x give the tx. In the same way, you can identify ty and tz also. So this is for simple image. I can move to the 3D object. This 3D object having different edge points. Here 7 edge points are there you can apply this formula for each and every edge points. Then you can get the new XYZ coordinate values for each edge points. Then you can connect these endpoints. Then you can get the shifted object. So in this way, 3D translation can be achieved. The next topic is parametric motion. So it is nothing but it represents the motion using the mathematical model by means of translation, rotation, scaling, etc. From this previous topic, we can visualize how the objects can be moved from one part into another part. In the same way, the object may be rotated, the object size may be changed, and the object may be distorted. For this any one of the method, the object's variations can be identified as motion. Here the translation can be represented as the mathematical model. So the parametric motion is nothing but it contains different 3D transformations. Transformation is nothing but translation, rotation and some other process. So in a previous topic, we only discuss about how the object is shifted from one place to another place. So we can say that translation alignment is one of the method followed in parametric motion. So parametric motion can be described in this way. The next topic is spline based motion. In motion analysis, we should tell in different time sequences how the objects can be moved smoothly. Because in real time, the movement is not a constant. For to make this smooth movement, we should need for splines. So this spline guide how the objects can be moved smoothly. So the spline is nothing but it is a smooth curve made by the joining of several points. I demonstrate this concept using Photoshop software. First I create one empty image. Here I want to draw the spline curve. So I can choose this tool, create some control points. So these are all the control points. Using this I can create some curves. So we can create any kind of curve using these points. Suppose I want to make this part also a curved one, means I can create a one more control point here and make it as a curve. Then I want to guide the particular object can be moved in this way. So this plane curves can be guide how these 3D objects can be moved inside the frame smoothly. The next topic is optical flow. In a real time, we already observed that this kind of scenario. When the object moved from one position, the other parts of the image also changed. So this optical flow identify these kind of changes. So if the object moves from one part into another part, the surrounding objects also changed over the time. That can be identified by optical flow. The next topic is layered motion. In real world, there are different objects present in the particular frame. These different objects can be considered as the different layers. For this methodology, we can easily control these layers to make a realistic movement of the object. So in this example, the background, road and car can be treated as the different layers. That variations can be calculated individually and combined together to make the particular scene. So in this way, we can achieve the better motion analysis for the 3D objects. So the layered motion is nothing but the different layers can be computed parallelly and combined to give the realistic movement illusion in a 3D objects. So all the topics are over. I conclude these topics. So in this unit, we studied about how 3D objects can be captured by different methodologies and visualized as the 3D objects by different techniques, and that informations can be stored inside the computer by means of different representation methodologies, and that can be reconstructed and recognized as again original objects. And movements of the 3D objects can be identified by the different methodologies. You can download the notes at the description. If you have any clarification, you can comment it. Thank you for learning with me.